Okay, so now we're going to take a look at when we have motion of a projectile with a launch angle other than 0. So when the angle at which projectile is launched is the launch angle, and the launch angle determines what the trajectory will be. And it can be anywhere from something straight down to straight up, and anything in between, really. The launch angle of 0 counts, but now we're going to look at when we have a launch angle other than 0. So if this is the motion of a ball, this could be an example of a ball that's being thrown up at an angle, and we have an initial velocity that is in an angle above the horizontal. And what we have to do is break up that velocity in the x and y, because we know that the motion in the x and y obey different laws of motion. And so if this is the initial velocity, we have to break up the x velocity initial and the y velocity initial. And then with those, we can look at the motion in the x and y separately, just like we did with a launch angle of 0 degrees. So this is also symmetrical, just like if we threw a ball straight up in the air. It spends half the time going up and the other half of it going down. And one of the key things that we're going to be able to use is we know in the y direction there's no velocity, or the y velocity at the top is 0. But in the x direction, and this is key here too, the x velocity does not change. There is no acceleration in the x as long as there's no air resistance. So this velocity in the x is the same the entire way. These should be perfectly horizontal lines. Sorry. And then in the y, it's getting, if you have an initial y velocity like this, it gets lower and lower and lower and lower, and then at the top it's 0, and then on the way back down it's symmetrical. It gets greater and greater and greater in the negative y, so that at the very end, this velocity and this velocity are actually the same magnitude. It's just the directions are opposite. So let's take a look at an example here. This is C21. A soccer ball is kicked with a speed of 9.5 meters per second, angle of 25 degrees, and the ball lands at the same level from which it was kicked. We want to find out how long was the ball in the air. So the first thing we want to do is set up in our picture here. We want to know the distance that it traveled in the x, and we know the initial velocity is 9.5 meters per second. Now, as you set this up, it's very important to draw out a separate triangle. Do not draw it up here. Okay. The reason is I see this all the time. I draw it here, and then you guys try to do trig or something to figure out this length or something. That's bad, really bad. Okay, so don't do that. Make sure over here you set up your x and y, figure out your x velocity, your y velocity, in this case using the cosine of 25 to get the x velocity, the sine of 25 to get the y velocity, and then what we're going to do is work out the x and y motion separately. So we're going to use the fact that the velocity at the top in the y direction is 0. We can calculate that, and the time halfway is 0.4097. We multiply that by 2 to get the time the full way. Then we can do the x problem where we bring in our x velocity and our time, and we can determine the displacement in the x, in this case 7.05 meters. So I'll have you try this one here. We have a golfer that's teeing off the golf ball, the speed of 42 meters per second. The initial direction is 35 degrees. And we want to figure out how far from the golfer does the ball land. And so we're going to need to figure out, how much time is it in the air first. And so what I want you to do, you can go ahead and draw this out first with the big picture, and then you're going to need to break up your velocity in the x and y. And then after that, see if you can determine the time halfway, then the time the full way, and then you can bring in your x problem and determine the displacement. So go ahead and pause the clip here and give this a shot. Okay, so if you want to check your x velocity and your y velocity here, 24.09 meters per second, and then the x velocity 34.4 meters per second. Time halfway comes out to be 2.46 seconds, multiply that by 2, and we can get the time the full way. And then with our x problem, we multiply our x velocity times that time, and so we know it's going to go 169.1 meters in the x direction. Okay, and so now I want to take a look at some motion graphs with this, and this is important to do. So go ahead and draw position in the y versus position in the x. So you can draw that, the first one. The second one is position in the y in time. And then the third one is position in the x in time. So after you draw those out, go ahead and pause the clip and determine, or go ahead and draw those, what those graphs look like as best you can, and then we'll talk about it. Okay, so if we look at position in the y and the x, this actually is basically a picture of what's happening as the ball goes across, or if this whatever projectile it is. Because we have position in the x and then position in the y, this is almost just like drawing a picture. The second one, the velocity, or the position rather, in the y, it starts at 0 and then goes up to a height and then comes back down. And if you notice, if we took, tangent lines along the way of this, at the top the tangent line would be 0 because the velocity in the y is 0. And then on the way down, if we took tangent lines, they get steeper because they get greater velocity in the y going downward. And then for our last one, this is a straight slope because if we get the slope of this line, we're going to get a constant velocity. And so the velocity in the x does not change, so the position over time would look like this. Now, if we were to draw out the velocity in the y and the velocity in the x over time, why don't you go ahead and try that? And so pause the clip, and then you can try that. Okay, so the velocity in the y starts out from 0, or rather, not from 0, from the initial y velocity, and then eventually becomes 0 at the top, halfway, at time halfway, and then at the full amount of time, it's at a certain negative velocity. So if we got the slope of this line, what would we get? We get negative 9.8, right? Meters per second squared. So the slope of that would give us this, and then hopefully you recognize with x, the x velocity does not change. So what it starts with, it'll finish with, and throughout that whole time period. Now draw the acceleration graphs for the y and acceleration in the x. And so pause the clip and then see how you do. Okay, so in the y, it is a constant negative 9.8 meters per second squared. That is the acceleration the entire time. And then in the x direction, there's no acceleration as long as the air resistance is 0. Now we're going to take a look at a situation where a ball is being thrown off from a certain height from a roof, and it's being thrown at an angle, and this is an angle of 25 degrees above the horizontal. At the same time, the ball is being dropped from the top. And so we're going to compare their speeds when they hit, and this is a problem where we're combining the projectile at an angle and also at a height. So for the snowball that's just being dropped, it's pretty straightforward. We have the initial height is 7, final height is 0. The final velocity we don't know, and that's what we're looking for in the initial velocity. It's being thrown downward at negative 13. So go ahead and pause the clip and determine the final velocity, and then we'll take a look at part B. Okay, so you should have gotten 17.498 meters per second is the velocity it hits the ground. Let's go ahead and take a look at snowball B here. So what we're going to need to do is break up our velocity in the x and y, because they obey different equations of motion. And the x, it's going to stay the same x velocity the entire time, but in the y, it's going to be 5.494. So what I want you to do is go ahead and solve for the final y velocity using the constant acceleration equations, and then what we're going to do is bring that together with the x to determine the overall speed. Okay, so for the x problem, the velocity stays the same, and then for the y problem, we know we're looking for the final velocity and the initial velocity, and the y is positive 5.494. And so what we would end up getting for the final y velocity would be 12.94. And then we bring that together with the 11, and we can get a resultant velocity of those two. And the resultant velocity of those two are the same, which is kind of maybe unexpected. So that's because, well, we'll take a look at that with the energy, but they come out the same because they started out with the same speed.